Hi one and all, I am Steven from Aero B section. Today my topic is applications of diffraction. Well, we all love rainbows after rain. We all know that light plays a key role in the formation of a rainbow, and there are many things about light which you may not know, and one of those phenomena is diffraction. It's an simple phenomena but still an important one. You may have seen some of the real life examples of diffraction in your life, but due to lack of proper knowledge about them, you may have not be able to recognize them well. Examples and applications of diffraction in real life: CD reflecting rainbow colors, holograms, sun appears red during sunset, from the shadow of an object, bending of light at the corners of the door, spectrometer, X-ray diffraction to separate white light. Real life examples and applications of diffraction. Before understanding how diffraction occurs in the real life examples, let's learn about diffraction first. What is diffraction? Lights behave like waves. If light waves encounter obstacles or a slit with a small gap, waves start propagating from that gap. That gap or diffracting aperture becomes a secondary source of propagating wave. Gap in the obstacles behave like a secondary source of the wave because light bends around a corner or obstacle, and this phenomena of a wave is called diffraction. We can go into the picture and take a minute at picture. Diffraction and interference are closely related, but they don't have an exact meaning. Diffraction is tend to be used when there are many sources of wave, and interference is used when only a few wave sources are considered. Diffraction fundamentals applications. Diffraction is a deviation from a straight path that occurs when a wave such as light or sound passes around an obstacle or through an opening. The importance of diffraction in any particular situation depends on the relative size of the obstacle and opening and the wavelength of the wave that strikes it. The diffraction grafting is an important device that makes use of the diffraction of light to produce spectra. Diffraction is also fundamental in other applications such as X-ray diffraction, study of crystals, and holography. When a source of wave such as a light bulb sends a beam through an opening or aperture, a diffraction pattern will appear on a screen placed behind the aperture. The diffraction pattern will look something like the aperture, a slit, circle or square, but it will be surrounded by some diffracted that gives it a fuzzy appearance. If both the source and the screen are far from the aperture, the amount of fuzziness is determined by the wavelength of the source and the size of the aperture. With a large aperture, most of the beam will pass straight through with only the edges of the aperture, causing diffraction, and there will be less fuzziness. But if the size of the aperture is comparable to the wavelength, the diffraction pattern will be done. For example, an open window causes sound waves to be diffracted through an angle. Fresnel diffraction. Fresnel diffraction refers to the case when either the source or the screen are close to the aperture. When both source and screen or far from the aperture, the term Fraunhofer diffraction is used. As an example of the latter, consider starlight entering a telescope. The diffraction pattern of the telescope's circular mirror or lens is known as Airy's disk, which is seen as a bright central disk in the middle of the number of Painter rings. This indicates that the image of always be widened by diffraction. Diffraction grafting. The diffraction of light has been cleverly taken advantage of to produce one of science's most important tools, the diffraction grafting. Instead of just one aperture, the large number of thin slits or grooves, as many as 25,000 pairings, are etched into a material. In making these sensitive devices, it is important that the grooves are parallel equally spaced and have equal widths. The diffraction grafting transforms an incident beam of light into a spectrum. This happens because each groove of the grafting diffracts the beam, but because all the grooves are parallel, equally spaced, and have the same width, the diffracted waves mix or interfere constructively so that the different components can be viewed separately. X-ray diffraction. X-rays are light waves that have very short wavelengths. When they irradiate solid crystal material, they are diffracted by the atoms in the crystal, but since it is a characteristic of crystals to be made up of equally spaced atoms, it is possible to use the diffraction patterns that are produced to determine the locations and distances between atoms. Simple crystals made up equally spontaneous of atoms diffract X-rays according to Bragg's law. Current research using X-ray diffraction utilizes an instrumental called a diffractometer to produce diffraction patterns that can be compared with those of known crystals to determine the structure of new materials. Allography. When two laser beams mix at an angle on the surface of a photographic plate or other recording material, they produce an interference pattern of alternating dark and bright lines. Because the lines are perfectly parallel, equally spaced, and of equal width, this process is used to manufacture allographic diffraction grafting of high quality. In order to reconstruct an image of the object, allography is also known as wavefront reconstruction. An illuminating beam is diffracted by plane surfaces within the allogram following Bragg's law, such that an observer can view the image with all of its three dimensional in detail. Thank you.